So these are the two transistors, I repeat. One is the NPN transistor, second is the PNP transistor. How you get this transistor? We'll take germanium or silicon, anything, either germanium or silicon. To this, on one side, suppose if you want PNP, on one side of it, we will dope phosphorus, sorry, what is it, boron. Similarly, on the other side also, we will dope boron, and in the middle, we dope arsenic or phosphorus. You know, boron, I told you already, extrinsic, while discussing extrinsic semiconductor, boron is trivalent. Even this is also trivalent. This is pentavalent. So what we are doing here, we are doping two trivalent impurities on both the sides of germanium and a pentavalent impurity in the middle. As a result of that, we will get three different regions. Those regions are this region towards the left, we call it as the emitter, and the region towards the right, we call it as collector, and the middle one is called base. So these are the three regions formed. I repeat once again, we took a pure semiconducting crystal, either germanium or silicon, and on both the sides, if you want PNP, a trivalent impurity is doped. In the at the center, a pentavalent impurity is doped. Thus, the two ends of the semiconductor germanium or silicon will become p-type. This is of course phosphorus. So the two ends where the trivalent impurity is doped will become p-type, and the central region will become n-type. Thus we will get this PNP transistor. This is what I explained. So whatever I explained here is nothing but this. Similarly, you take pure germanium or silicon. Yes, on one side, at the two ends, we'll dope phosphorus, and in the middle we dope boron. Therefore, a pentavalent impurities are added at the two ends of the pure silicon or germanium. Therefore, these two will become the n-type extrinsic semiconductors, and the central portion where boron is doped will acquire p-type. So thus we will get the n-type extrinsic semiconductor. This is what I mean. So thus, we have two different types of transistors. One is the NPN transistor, second one is PNP transistor. You know, I don't know how many of you, how best you remember the concepts what we discussed the other day. In N, we have the electrons are the majority charge carriers. Yes or no? Do you remember or not?
Yes.
And P, we have the holes. N region, electrons are the majority charge carriers. P region, holes are the majority charge carriers. So, the direction in which holes move, the direction in which electrons move will be opposite to conventional current. Therefore, this is how when you bias it, when you apply voltage, we'll have the holes will be moving towards the base. Sorry, electrons will be moving towards the base and holes will be moving away from the base. Therefore, the arrow mark, if it is directed away from the base, then that is that is a symbol of NPN transistor. Arrow mark indicates the movement of the holes. So when it is biased, means when some suitable voltages are applied across the two junctions, then the holes will be moving away from the junction, so which is shown by this arrowhead directed away from the base. Therefore, this is the NPN transistor, whereas in PNP, yes, holes will be drifting towards the base. Electrons from N region will be moving away from the base. So, the direction which the positive ions will move, or the direction opposite to electron motion, will be the direction of the conventional current. So, the holes are moving towards the base, means here the arrowhead is directed towards the base. So, this is the circuit symbol for PNP. So, we have designed two circuit symbols based on the direction of the conventional current which flows through these two transistors. And second thing is, you must have identified, we have emitter and base and collector. We call this emitter and base, the common region of emitter and base, we call it as emitter base junction, and the other region which is common to both base and collector, that is called base collector junction. So in both the transistors, we'll have these two junctions. And another important point is junction J1, that is, please make the points, note down the points. Emitter base junction will be always in forward bias, and the base collector junction should be always in reverse bias. Another thing, if suppose VBE is the voltage across emitter base junction, VBC is the voltage across base and collector junction, then you must also remember that this VBC should be greater than VBE. So the reverse bias voltage applied across the base collector junction should be more than the forward bias voltage applied across base emitter junction. There is a reason for that. The reason is all the charge carriers diffusing from emitter through base into the collector must be swept into the external circuit, so that whatever operations you are expecting from the transistor will be performed successfully. So for this, we ensure that the base collector voltage will be always greater than the reverse biased base collector voltage will be higher than the forward biased base emitter voltage, or you can also say output voltage should be higher than the input voltage. So this is about the beginning of the transistor. Now we'll use this transistor in three different modes. So let us see those modes. Have you noted down all the points? So first point.
1 minute, sir.
Minutes.
The literal meaning of transistor is trans plus resistor. So this device transfers the resistance appropriately across the junctions for achieving high current gain, high voltage gain, and high power gain. So the physicists who designed it, initially it was Bardeen and Brattain, and later it was Shockley. So these three involved in designing the transistor. So what is transistor? How many types of transistors are there? And what are how the voltages are applied across the two junctions? And what are the circuit symbols? That's what we have learned here now. So this is first, what is transistor? And this is second, how many types of transistors are there? This is third, how they are biased. Diagrams, are they clear?
Yes, sir.
Okay.
Yes, sir.
E for emitter, even the written in complete form also. E for emitter, B for base, C for collector. If you are completed, please tell me. I will proceed to next. One more point is there in this circuit symbols. Already we have given the circuit symbols. So these two are the circuit symbols. How they are shown in the circuit means this is how we show them.
Noted, sir.
Noted, good. All points are simple and important. Now we'll do the circuit symbols. Three configurations are there. Okay. Yes. The first one, what I explained just now, this is common base. PNP transistor is shown. So this is the input voltage. It is applied across emitter and base. Are you able to see? Base
Yes,
is
sir.
common for input and output circuits. So input is applied here and output will appear here. So emitter and collector are present in the input and output circuits while base is common to both. Do you agree or not? Correct?
Yes, sir.
Sai.
Yes, sir.
The base is common to both input and output circuits. Hence, this is called as common base configuration. What do you call this? Common base configuration. Now coming to this. What is common to both input and output circuits? Yes? This is emitter. This is base. This is collector. Emitter, base, collector. So input is applied across emitter and base. Output is applied across emitter and collector. Input is applied across base and emitter. Output is appearing across emitter and collector. Therefore, this circuit is called as common. Emitter is common to both input and output circuits. Hence, it is called as common emitter configuration. Then coming to this. Yes. Now you can have a clear look. Again, PNP transistor. You can show the conventional diagram without circuit symbol also. You can show it. This is base, and this is emitter. This is collector. So input is applied across base and collector. Output is appearing across emitter and collector. So collector is common to both input and output circuits. Hence, this is called as, yes, tell me, common
collector.
Common collector. Yeah, if you want to note down, you can note down. Make it fast. Don't waste much time on the diagrams because there are many concepts to be done. This is common base configuration, common emitter configuration, common collector configuration. The transistor that is shown is PNP. Remember, in PNP transistor, yes, arrowhead is directed towards the base. So this is emitter, this is base, this is collector. Input is applied here, output is appearing here. So for this is called input circuit. This is called output circuit. So base is common to both input and output circuits. Hence, this is called as common base configuration. The same thing. If emitter is common to both input and output circuits, common emitter configuration and common collector configuration, then we may get doubt. Will we use all these three? Answer is no. We prefer mostly common emitter configuration only. Is the most preferred configuration. Reason is also there. Among these three, the very purpose the transistor is basically for high, already I told you, high current gain, high voltage gain, and high power gain. So these high values of the gains are possible only in the common emitter configuration. Common base and common collector won't be giving us those high value of gains. Hence, we prefer only common emitter configuration in all the electric circuits. Understand?
Yes, sir.
Okay.
Yes, sir.
Have you finished?
Completed, sir.
Good. Pranav, completed? Huh?
Yes, sir.
Good. Okay. Now the next. Second one, biasing. Biasing of the transistor. So first we are doing PNP transistor. So for this you should have the idea of P will have the P-type extrinsic semiconductor is formed by, yes, adding a trivalent impurity boron to a pure semiconducting crystal. Pranav, Sai, are you able to say this?
Yes, sir.
Yes, sir.
Yeah, to save the time, just I am preferring these diagrams because drawing all these diagrams, representing holes and all will consume lot of time. That's why I prefer this method. So P will have the majority charge carriers holes. These are all the holes. You can see. This is emitter. This is collector. This is base. Now, how to identify which is emitter, which is base, and which is collector? Are they identical? Means answer is no. Why they are not identical? Because emitter is heavily doped. So doping concentrations are very high. For example, it may be 10 to the power of 15 atoms per centimeter cube. So the emitter is heavily doped. The reason is the charge carriers are steered by the emitter. The movement of charge carriers in the circuit for making it to achieve the required operational performance of gaining something, current gain, voltage gain, in turn power gain, is achieved only the function begins from the emitter. The activity begins from the emitter. Therefore, emitter is heavily doped. Next, base. The base is a platform intended for providing the diffusion path for these charge carriers from emitter to collector. Therefore, if the base is very thick, then recombinations of holes and don't go away. I'll re-log in again. Okay. Yes. So to prevent the combination of holes and electrons in the base region, the base is kept very, very thin. You can see in the diagram also. So that the charge carriers from the emitter will diffuse into base and are pulled into the collector. For that, base is kept very, very thin and the doping is very low doping levels. And third one is collector. The collector is moderately doped. You need not have high doping concentrations, maybe around 10 to the power of 12 atoms per centimeter cube. That is here, for every 1 centimeter cube volume of the pure semiconductor, 10 to the power of 15 boron atoms are added for emitter. Just for example, I am telling. Similarly, for every 1 centimeter cube of boron, 10 to the power of, for every 1 centimeter cube of pure germanium, 10 to the power of 12 boron atoms are added. So the doping concentration is very high in the emitter, whereas it is very low, it is moderate in the collector. Whereas coming to this may be around 10 to the power of 8 per centimeter cube. So it's very, very low. That's about the difference in doping concentrations. It's common for both the PNP as well as NPN transistors. Then what happens is, see here, P is connected to positive. Okay. P is connected to positive. This is P region. This is positive terminal of the battery. And this is N. This is connected to negative terminal of the battery. This is called input circuit. Input is applied between base and emitter. So this is input. So input is applied between base and emitter. So the input circuit, I said it should be in forward bias. Therefore, P is connected to positive, N is connected to negative. And this is output. Output we have appearing across base and collector. So that is N and P. So it should be in reverse bias, I said. P is connected to, see this P is connected to negative and this N is connected to positive. So it is in reverse bias. This emitter base junction is in forward bias. Base collector junction is in reverse bias. So what happens here is electrons, at the center we have N. N-type extrinsic semiconductors, majority charge carriers are yes. Emitter is P. Collector also is P. And base is N. So here holes are the majority charge carriers in emitter and collector, and base electrons are the majority charge carriers. So what is happening here is, because of the forward bias voltage applied across the emitter base junction, electron will start moving into the emitter while hole starts moving towards the base. They start moving in opposite directions. Plus this this forward bias voltage will also give some energy to the electrons in covalent bonding. Other day I have explained you by diagrams. This is germanium, germanium, germanium atoms. These are all the germanium atoms in pure semiconducting crystal. And this is how the electrons are in covalent bonding with the germanium atoms. So these are the covalent bonds. No electron is free in the crystal lattice. All are in covalent bonding with the neighboring germanium atoms. But because of this energy, because of the biasing, some temperature increases across in the P region. As a result of that, these covalent bonds will be breaking. So once the covalent bonds break, large number of electrons will be released from these covalent bonds. And here you have a positive terminal. So all these electrons are pulled out of this emitter to start flowing in the circuit. And here at this junction, few of the electrons will go into the base. Leftover electrons are pulled by the collector because these holes will diffuse the base and enter into the collector. And already some more holes are there. So these electrons, majority of the electrons, 90 to 95% of holes will cross from emitter to collector via base. So these electrons will go and combine with the holes, thus they complete the circuit. Means now the PNP transistor starts functioning. This functioning mode of PNP transistor is only called as biasing. So what I said is the emitter base junction is in forward bias, base collector junction is in reverse bias. And here we are going to define the current gain alpha as change in collector current to change in emitter current. Plus one more thing you can see, collector, this is the emitter current is going into the transistor, base current is coming out of the transistor, collector current also is coming out of the transistor. So applying the conservation of charge, we can write the equation I is equal to IB plus IC. So the emitter current will be the sum of the base and collector currents. Okay, I'll just conclude and log in back again. Don't go away.